Okay, so then I guess we can start. So welcome everybody to the second talk today, and we will hear of the talk is towards multidimensional localization, and the speaker is Krzysztof Ciosmak, sorry, and so please you can start. Thank you.
Thank you very much for introducing me, and let me thank Robert McCann and Christina Somani for their kind invitation to speak here. So let me start. So first, let me start with a few words of historical introduction. So the story, I will speak about localization, about some generalization of one-dimensional localization to multiple dimensions. So let me first say something about one-dimensional localization. So it all started with Pine and Weinberger, who used this method to Poincaré inequality on convex bodies with log-concave measures on them. So we have a closed convex set and a function which is in C1 on this set, and it integrates to 0 against some log-concave measure mu on this set K. So a measure is log concave if its negative logarithm is convex. So then the Poincaré inequality holds true that the integral of f squared d mu is bounded by some constant times the norm of sometimes the integral of the squared norm of the gradient for some Poincaré constant which is bounded in this way. So it's bounded below by pi squared divided by the squared diameter. And the idea of Pine and Weinberger was to use Borsuk-Ulam theorem. So here is a picture which shows what is the situation. We take some point in the relative interior of K, and for any vector V, we consider a hyperplane which is perpendicular hyperplane to this vector, and we define a function capital F of V to be the integral on the intersection of K with the positive, with H plus, which is 1/2 of the plane. And then, because f of V is equal to minus f of minus V, and this is a map from the sphere to real numbers, then by the Borsuk-Ulam theorem, we can infer that actually there is some vector for which these two integrals coincide. And then it's trivial to observe that it suffices to prove this inequality for these two separate cases. And so this Borsuk-Ulam theorem works as long as the dimension of K is at least 2. Because otherwise we would have just zero-dimensional sphere and we would not be able to use Borsuk-Ulam theorem. And actually, with some technical effort, it allows us to show that this technique will produce a measurable partition of our space, such that if we consider conditional measures of our measure mu with respect to this partition, then there will be log concave. And of course, the integrals of these conditional measures will be 0. And therefore, it will suffice to prove this inequality in one-dimensional case. So this was the background. And now let me speak how this was further generalized to the Riemannian manifold setting and also to the metric measure spaces setting. So this localization technique was used in convex geometry to basically to reduce some complicated n-dimensional problem to a collection of one-dimensional problems. And applications thereof include various geometric and functional inequalities, as you have seen. It includes Poincaré inequality. And we have seen that these developments, they employed Borsuk-Ulam theorem and were only possible to use in the Euclidean setting because we used the Borsuk-Ulam theorem, and for general Riemannian manifolds, let's say there is no, it's not possible to, well, at least I don't know of any such developments that would know such analog of Bohr-Coulomb theorem that would work in Riemannian setting. So in 2013, Boas-Klartak has come up with an idea how to generalize this technique to Riemannian manifolds. And this generalization used optimal transport with respect to the metric cost function. And it has been further conjectured by Boas-Klartak that this method can be further generalized to multiple constraints setting, which I will speak about later on. And some parallel generalization was the following. So Ota has generalized this technique to Finsler manifolds, and Cavaletti and Mondino have generalized this to metric measure spaces with CD condition. So let me first speak how optimal transport is used here. So we assume that M is an n-dimensional weighted Riemannian manifold, so it's equipped with a measure, and we assume that we are given a function M which integrates to 0 against this measure, and it is integrable. It has integrable first moment. And we will consider optimal transport problem of transporting the measure eta 1, which is given by the function f, which is given by the density f plus with respect to mu, and eta 2, which is given by the density f minus with respect to mu. And the optimal transport we consider with respect to the metric cost. And actually, what would be more useful to us will be the dual version of the optimal transport problem, which is the Kaczorowicz-Rubinstein problem. And the problem is to find a maximum of such integrals where the maximum is taken among all one Lipschitz functions from our manifold to real numbers. Sorry. So let me. So as I said, that was a maximizer because obviously by Archer-Ascoli theorem there exists a maximizer, and if we take such a maximizer, we can now connect to the talk of Boas. So for any, this will be one Lipschitz function, and we can speak of the transport rays. So for me, a transport ray, it will be a maximal set such that if we restrict this function v to the set, then it will be an isometry. So this will be an isometry on this set into the real numbers. It doesn't have to be surjective. And the transport set will be simply a Borel union of some transport rays. So here is a little example. If we take V to be the norm, then this is what we will see. So we'll see that these transport rays are simply the half lines stemming from the origin. So then there is the following mass balance condition which holds true, namely that if we take any transport set, then the integral of f with respect to mu will be 0 on this transport set. And these transport rays will form a partition of M into minimizing geodesic up to a null set. So there might be a set of Lebesgue measure 0, which will contain points which belong to two distinct transport rays. But this doesn't happen in the relative interiors of transport rays. So if you have a point in the relative interior of transport ray, then it belongs to a unique transport ray. And we may disintegrate our measure mu with respect to this partition so as to obtain such a mixture. And from this mass balance condition, it immediately follows that the integral of f against the conditional measures will be 0 for almost every transport ray. And if we had originally mu defined on Euclidean space such that it was log concave, then also the conditional measures will be log concave, and they will be concentrated on the relative interior of the transport trace. And the following also is true, that if we have the log concave measure, so as I said, if mu was log concave, then the conditional measures will also be log concave. But the following, more is even true. If our initial manifold satisfied curvature dimension condition, then the conditional measures will also satisfy the curvature dimension condition with the same parameters. So let me briefly remind you what is a curvature dimension condition in this setting. So we have two parameters, k in real numbers and n, capital N, in this range. Then we assume that the Ricci curvature on vector for any vector v in the tangent space plus the Hessian of rho, where rho is the negative logarithm of the density of our measure, minus such factor is bounded below by kappa times the metric tensor. So if we consider our situation on flat space, then the Ricci tensor is gone. And let's say if we take capital N to be equal to infinity and kappa equal to 0, then we see that this is precisely the bound for the Hessian, and we see that this is equivalent to log concavity of our measure. And intuitively, the curvature dimension condition may be understood as a condition that the Ricci curvature is bounded from below and the dimension is bounded from above. So as I said, a result of Bas-Klartak is that if mu satisfies curvature dimension condition, then the conditional measures will also satisfy the same condition with the same parameters. And this method was applied to problems with one linear constraint. So namely, if you had this weighted Riemannian manifold and some function which integrated to 0, then we could conclude that there is this partitioning, and we could reduce our complicated problem to collection of one-dimensional problems. Now, the question was whether this can be generalized to several linear conditions. So if we suppose that we have some functions f1 up to fm, which all integrate to 0 against mu. So the question is, does there exist a partitioning of m into perhaps m-dimensional pieces for which the related conditional measures would have 0 integrals against f1 up to fm? And would it be also possible for the pieces to retain the curvature dimension properties of the original manifold? And there would be plenty of possible applications if such thing was feasible. This would include bounds for higher order eigenvalues of Laplacian, applications to multi-bubble conjectures, Gromov-Weiss inequality, also Bergen's hyperplane conjecture and isoperimetric conjecture of Cannon, Lovász, and Simonovitz. And such a generalization in the Euclidean setting was conjectured to hold true by Klartak. So let me speak about the first conjecture. So we assume that eta is a Rm valued vector measure on Euclidean space with finite first moment and with total mass 0. So for example, in the setting of the previous slide, we take some, let's say, probability measure mu and some m functions which integrate to 0, and we can cook up such vector valued measure. And then we consider a generalization of the previously considered optimization problem, which is now we integrate one Lipschitz maps from Rn to Rm with respect to our vector valued measure, and we look for a map for which this is maximal. So again, as before, this problem admits a maximizer by Artella-Scully theorem. So we take this maximizer and we can generalize the definitions that we had previously to our setting in the following way. So we will say that S in Rn is a leaf whenever it's a maximal set, such that if we restrict V to S, then we will get an isometry. So in the previous setting, transport rays, which are a lower dimensional version of leaves, were only either one-dimensional or zero-dimensional. And here, the dimension of a leaf can be anything from 0 up to m. And A will be a transport set whenever, again, it's a Borel union of some transport of some leaves of V. And if we suppose that our vector measure eta is absolutely continuous with respect to the Lebesgue measure lambda, then Boas-Clarta conjectured that eta of any transport set will be 0. So it would be a direct generalization of the mass balance condition, which was studied by Evans, Gangbo, and so on. And this, unfortunately, is false in general if we consider vector valued measures, well, genuinely vector valued measures, so not simply signed measures, but vector valued measures. And even if we would like to relax this problem and think that maybe if we replaced the set of one Lipschitz functions by some subset of one Lipschitz functions, then maybe this could be true. But unfortunately, it is false for any subset of one Lipschitz functions that we take here. Okay, so how the mass balance condition can be proven in the one-dimensional case. So one option is to use the duality with the optimal transport. So let me speak how this could have been generalized to the vector valued setting, and how can we get some conditions under which, whenever they are satisfied, the answer to the conjecture of Clartak is true. So we again assume that n eta is an Rm valued measure on Rn with total mass 0, and we assume that it has finite first moment. And then the optimization problem that we considered in the previous slide, then it has a primal problem, which is the following vector valued optimal transport problem. So we consider infimum of integrals of the following kind. So pi belongs to the set gamma of eta, which is the set of vector measures on the product, for which, if we look at the difference of the marginals of this vector measure, then we get eta. And here we integrate with respect to the total variation of pi. And then, as I said, these two problems are dual to each other. Namely, this infimum is equal to the supremum that we considered before. So this x here should be Rn. So let me suppose now, again, that eta has finite first moment and total mass 0, and suppose that V is an optimal potential for eta. And now let me suppose that there exists an optimal transport pi, which not only is optimal, but also the marginals of the total variation are absolutely continuous with respect to the Lebesgue measure. So this condition in the one-dimensional setting is satisfied if eta is absolutely continuous, because the duality that we have in the setting of signed measures is actually stronger than the one that we have here. Namely, we have duality with such minimization problem, but pi, this gamma of eta, has to be replaced by the set such that the first marginal of pi is equal to eta plus and the second is equal to eta minus, so that these marginals and pi are non-negative measures. So this, we see clearly that the marginals of the total variation are automatically absolutely continuous if eta is continuous, absolutely continuous. Okay, so actually, if this condition holds true, then indeed it's true that for any transport set A associated to our optimizer, the total mass is equal to 0. Okay, so let me now pass to the second part of this story about multidimensional localization, namely the curvature dimension conditions. So the first point is, similarly as in the one-dimensional case, the leaves of any one Lipschitz map, they form a partition of the underlying space, and this is up to a set of Lebesgue measure 0. So, and they are also closed and convex, and the dimension is at most m. So this is perhaps a picture that can show how this could look like. And we may, of course, as previously, disintegrate our vector measure with respect to this partition. And what is true is that if eta, so this eta should be the total variation of eta. If total variation of eta satisfies the curvature dimension condition, then also almost every leaf S of dimension m will also satisfy the curvature dimension condition with the same parameters, and it will be concentrated on the relative interior of the leaf. So here let me stress that I do not know whether this holds true for leaves of lower dimension, and there might be leaves of lower dimension. So this partially resolves another conjecture of Klartak, this time in the affirmative. And let me speak about the idea of the proof. So the idea is to build upon a work of McCann, Caffarelli, and Feldman, and we will perform basically change of variables, which will rectify our picture. So this is the precise formula that I will consider. So here we have this leaves of our one Lipschitz map V. We consider its level set V equal to constant. So unfortunately, I'm not able to depict here 4-dimensional picture. So the level set will be simply 1-dimensional, but it might be of higher dimension. So here we see that the level set passes through any leaf of our function V, and here we consider rectified leaves, and we look at the following map. So R is a local parametrization of a fiber; it's Lipschitz, and well, dV is the derivative of our Lipschitz map, and we consider this map to, so this point A naught goes to R of A, and AB in this leaf goes to F of AB. So this function is linear on the leaves of V. It's not only linear, but it is an isometry. So then we perform this change of variables, and on any leaf, we go back with the change of variables. We do some calculations, and it turns out that using Cauchy-Schwarz inequality, we can get the curvature dimension condition. Basically, this is the rough idea. But perhaps the key point is that this formula provides a local diffeomorphism. So let me now speak more about the idea of the proof. So if we denote the orthogonal projection onto the tangent space to a leaf containing x by p of x, so any such leaf, it's a convex set in our N, so it has a tangent space, and we can look at the orthogonal projection on that tangent space. So this will be p of x. And by the area formula and Fubini theorem, the density on the leaves is multiplied simply by this absolute value of this determinant. And here we see the second fundamental form of the fiber, which is perhaps interesting that it pops up here. And another key point is the regularity of our map V, and moreover the regularity of the dV. So we want to differentiate it. So we want to have the second derivative of v, and the initial assumption is that the v is only one Lipschitz, so it does not necessarily have the second derivative, but it turns out that in the relative interiors of n-dimensional leaves, the derivative is Lipschitz itself, and moreover we have this interesting strengthening of the one Lipschitz condition for v. So if this was 0, if we had 0 here, then we would simply read out the one Lipschitz condition for v. But actually, if we are in the relative interior of the leaves, we can put here this factor, which also tells us that the derivative is Lipschitz, at least locally, if we are away from the boundaries, relative boundaries of the leaves. Fine. So I have spoken about the situation in m dimensions, but we would like to have complete picture for n-dimensional leaves. So what is the difference if we consider lower dimensional leaves? So well, in general, the derivative for any point in the relative interior, the derivative will be an isometry on the tangent space V of the leaf, and it will be independent on the choice of V, because it will be just linear. It's isometry on the leaf. This is how leaf is defined, so it will be this linear isometry. But it might happen that it can be an isometry on a strictly larger subspace. So here we have this picture. So here is our leaf, here is our point, here is the tangent space to a leaf, which is this plane. And here we can consider any point W, which is, let's say, perpendicular to our tangent space. And it might happen that the derivative at x is also isometric on the vector W. And actually, it turns out that there exists a maximal subspace G on which derivative of V is isometric, and it is independent on the choice of the leaf. So if you had such a W for which derivative of V was isometric on W, then if we had any other point, then the derivative will also be isometric on that other point. So I termed such subspaces ghost subspaces because they play a role in this partitioning, yet they are not visible on the level of partitioning. So they are called ghost subspaces, and I will say that they are trivial whenever they are equal to the tangent space to a leaf. So triviality of ghost subspaces accounts to the assumption that there are no such directions on which the derivative is isometric, which are perpendicular to the tangent space V. So what I can prove is that if you assume that for a given leaf S, the ghost subspace is trivial, then also the conditional measures with respect to this partitioning for this particular leaf, it will be absolutely continuous with respect to the Hausdorff measure of the correct dimension. So this is like a first step in establishing the curvature dimension condition for lower dimensional leaves, at least with trivial ghost subspaces. Well, because this is of course necessary, because if weighted manifold satisfies curvature dimension condition, then necessarily the measure is absolutely continuous. It has a density e to power minus rho, so it's absolutely continuous. And even more is true if all the ghost subspaces, if we have some vector measure eta, and we assume that all the ghost subspaces for the optimal potential for this vector measure eta are trivial, so it's not possible that there is this pathology, because this is kind of a pathology. It's easy, but it's not trivial to cook up an example for which those subspaces occur for leaves of positive measure. So if this pathology is not present, then there exists actually an optimal transport with suitable properties, and then the mass balance condition holds true. So in such a setting, these two conjectures of Klartak would hold true. Fine. So there is also another proof of the mass balance condition in the setting of one-dimensional measures, of signed measures. And now let me speak what's the difference, how the one-dimensional mass balance condition is proven, and why it doesn't work, why this proof doesn't carry over to the multidimensional setting. So, well, in the one-dimensional setting, we have the following theorem about extensions of one-Lipschitz functions. So we have a set, if we have set A in Rn and V defined on the entire space, and we assume that V is one Lipschitz function, and we have another one Lipschitz function U defined only on the subset, and we would like to extend the one Lipschitz function to the entire space. Well, this is possible by classical Max-Chain formula, but we would like also to extend it in such a way that the supremum distance from U to V on the set A is preserved for the extension. So we would like that the extension U tilde be in the same supremum distance as was U to V on the set A. And this is actually possible, and the proof is 2 lines. So we take any one Lipschitz extension U to the entire space Rn, and this is possible by, let's say, Max-Chain formula, and let delta denote this supremum distance from U to V on the set A. And then we can simply take U tilde to be equal to U tilde prime maximum V minus delta minimum V plus delta. So clearly this definition doesn't change U tilde on the set A, because by the definition of delta, and clearly suprema and minima and maxima of one Lipschitz functions are again one Lipschitz, so this is still one Lipschitz function. So we have found a one Lipschitz function that satisfies these two conditions that we wanted. Okay, so how, using the previous result, how can we prove the mass balance condition in the one-dimensional setting? So again, let V attain this maximum. So this proof, let me remark here, it's due to Boas-Klartak. So we take a transport set A in the manifold M, positive epsilon, and the compact set K in A, which almost exhausts the integral of f with respect to mu, so that the integral of f d mu on A minus K is at most epsilon. So here is a picture. Here we have this transport set A, we have this compact set K, and we will also have K delta. So K delta will be the set of points for which this inequality is true, and this means that the function V is for points X and Y is not only Lipschitz, but it's better than Lipschitz, and the delta quantifies how much better it is. And having this set K delta defined, we can define another one Lipschitz function U delta naught by the following formula. So this will be a one Lipschitz function on K union K delta. So on K delta, we simply retain the values of function V that we had initially, and on K we put V plus delta. Then by the very definition of K delta, this will be a one Lipschitz function, and it will be within delta distance to V on K union K delta. And then we, using the previous theorem, we may extend, the function U delta naught to entire manifold to a one Lipschitz function U delta, which will be within delta distance to V. So this is precisely where this ingredient comes into play. And we observe that actually the union of K deltas is equal to our transport set, except a set of points that could belong to two transport rays of V. So we are in the one-dimensional setting, so transport rays so leaves are called transport rays. And the set, as I have already said, the set of points which belong to at least two different distinct transport rays is of measure 0, and this follows by the fact that V is not differentiable at this point. Fine. So using this, well, U delta is a competitor to V in this problem. So clearly we have such inequality that integral of V times F with respect to mu is greater or equal than V times F with respect to mu. So we can subtract and divide by delta. And thanks to this bound on the supremum distance, this is bounded by 1 always. So we can then send delta to 0, and what we will get is simply that the integral of F on the set A with respect to mu will be bounded below by minus 2 epsilon, and this minus 2 epsilon comes only from the fact that our set K was not the entire A, but some compact set which almost filled A in terms of this integral of F with respect to mu. And repeating this procedure, where we put minus delta here in place of delta, we would get the other inequality. So here we of course send epsilon to 0. And then we get the other inequality, and we infer that the integral of F with respect to mu on any transport set is equal to 0. All right, so what we would need in the multidimensional setting would be an analog of this theorem for multiple dimensions. So we would need to find a theorem which would allow us to extend one-Lipschitz vector values maps to the entire space with some bound on the perhaps supremum norm or similar thing. But it is not even trivial to find any extension, and it's actually a theorem of Kirschbaum from 32, that if you have a set X in Rn and V on this defined on that set, which is a one-Lipschitz map, then there exists a one-Lipschitz extension V, one-Lipschitz extension of V to the entire space. And this, well, the crucial thing here is that the norms with respect to which we consider the extension are one-Lipschitz, are Euclidean. Okay, so let me consider the higher dimensional setting. So we assume that M is at least 2, and we have any map from Rn to Rm. And then the following two conditions are equivalent. Is there a question? No. So the first condition is that whatever set in Rn we take, and whatever one-Lipschitz map on the set A with values in Rm we take, then there would exist one-Lipschitz extension U tilde from Rn to Rm, which would preserve the supremum distance to V in this sense. So this condition in the one-dimensional setting is satisfied by any one-Lipschitz map V. And yes? No condition. Yes. So this first point is equivalent to that V is one-Lipschitz and affine. So if we want to do what was possible for any one-Lipschitz function in the one-dimensional setting, but if we want to do that in the multiple dimensional setting, then this is only possible whenever V is affine. And actually, we can describe more quantitatively the rate of continuity, which will allow us to, well, which will give us the bounds which can be attained in this extension problem. So we consider the following situation. So we have two sets A and B. One is contained in another, and both are contained in Rn. And we have a one-Lipschitz function V from Rn to Rm. And we define the following quantity. So dv of AB will be the supremum of distances of v of x to v of y, where x is in A and y is in B. And we have then the following theorem. So we assume that U is defined on A, it has values in Rm, and it's one Lipschitz. And let's assume that it is within delta distance of to V on the set A. And then what we can do, we can extend one Lipschitz map U to a one Lipschitz map on B in such a way that the supremum distance will be bounded from above by the square root of delta squared plus 2 delta dv of AB. So we see here that this dependence, if delta is small, this dependence is of the order square root of delta. So we cannot do the proof that we did in one-dimensional case to obtain mass balance condition, because there we divided by delta and we would have something that blows up to infinity. And actually that rate of continuity is optimal. So we assume again that m is greater than 1, strictly greater, and we define two functions, u and v, as in the following picture. So yes, so we have 2 points, 3 points, x, y, and z. So A will be subset of Euclidean space consisting of 2 distinct points, x and y, and B will consist of these points and also their midpoint. So z is equal to x plus y by 2. And let's denote by 2a the distance from x to y. So we put u of x and u of y in some two-dimensional plane so that they are in distance 2a from one from the other. And we define v in the following way. So we take a triangle, triangle with equal length of 2 sides here, and these 2 sides have length a plus delta. So we produce such a triangle. One of these vertices we call v of z, and 2 points on these sides we call them v of x and v of y. They are in a distance a from this vertex v of z. So what happens then? Because u of x and u of y are within distance 2a from one of the other, and the same is true for the points x and y, then necessarily any one Lipschitz extension u tilde of u to the point z will also have to be the midpoint here. So u tilde of z will have to be a midpoint of u of x and u of y. There is no other possibility. And this actually produces a one Lipschitz extension. And then we just simply compute this distance of u tilde of z to v of z. And what we get is that this is precisely delta squared plus 2 delta a. So if delta is greater or equal than a, this is precisely the quantity that we had in the previous theorem. If delta is not greater or equal than a, then asymptotically this is also true, but it's not as nice and neat as it's here. But also the asymptotics will be as square root of delta. Yes, so perhaps I have still a couple of minutes. So I could perhaps speak why this first conjecture of Boas is false. And this I could, unless there are questions that would take a bit of time. Yes, please.
In the case where, let's ignore the case where there are ghost subspaces, are the induced measures on the leaves in top dimensions? Are these polynomial functions?
the induced measures in the setting, but are you asking about the top dimension?
Top dimension, yes, top dimension.
But then, well, in the top dimension, the ghost subspaces are trivial because there is no space for.
Are the densities polynomial on each needle, on each pancake?
Polynomial in.
Polynomial function.
Okay.
Because in the one-dimensional case, they are polynomial. Okay. Okay.
This I don't remember, but this might be plausible.
Okay. And one more question. So it seems like the optimization problem that I suggested was not the right one. Maybe?
Yes.
So are there other optimization problems around it which could be more?
Yes.
useful?
Yes. Well, I'm working in this direction, but I'm afraid I don't have any result that is any work that is mature enough to speak here about it.
Okay, thank you.
Are there any more questions? Okay. If not, then I can perhaps present proof why the conjecture of Boas, this first suggested problem is not the best one in this setting. So let me go back to the formulation. Okay, so here is the setting. So we have again an Rm vector valued measure with finite first moment and total mass 0, and we would infer that the total mass of any transport set is 0. And why this is not necessarily the case. So what we'll do, we'll produce some counterexample. So we assume that M is at least 2. And we assume that the conjecture holds true. So let x1, x2, and x3 be points in Rn. And we have three vectors in Rn. So it suffices to take three vectors, whatever M is here. And we also assume that they sum up to 0. And they are also in general positions. So these vectors are something like this. And then we take eta 0 will be our vector valued measure, will be the sum of vi times Dirac deltas at points xi. So x1, x2, x3. It could be like this: v1, v2, v3. And then we would like to consider some absolutely continuous measures. So we need to make this Dirac deltas, let's say, a cloud of points. So for any epsilon, we take mu epsilon to be simply the measure given by the sum of vi's times the normalized Lebesgue measures on balls of radius epsilon centered at points xi. Fine. And then, well, as I have already discussed, the minimizers, the maximizers in this dual problem here, they always exist. So let us, for any new epsilon, let me take u epsilon to be the maximizer. So a maximizer, there might be many. Fine, and then if we take this decomposition into leaves, then the conjecture tells us that total mass of any transport, say, of any transport set will be 0. Fine, so let me draw another picture here. So this will be x1 here, x2, x3. Fine. So let n I epsilon denote the set of all non-trivial leaves that intersect ball bxi epsilon. So this is so by non-trivial I mean at least one-dimensional. Well, this is a Borel set. It's a union of some leaves of the map U epsilon. Therefore, by the assumption, so we assume that the conjecture holds true, the new epsilon measure of the set is 0. Perhaps I can move here. Fine, and what does this mean? This means that Vi times lambda of Ni epsilon intersected with B of Xi epsilon, this is 0. And well, these vectors Vi were chosen so that they are in general position. It means that if such combination of these vectors is equal to 0, then all of these numbers have to be equal. Perhaps this should be J, sorry. And well, there are some non-trivial leaves of U epsilon. Therefore, the intersection of Ni epsilon with B of Xi epsilon, it has positive measure. And therefore, there are leaves of U epsilon that intersect the other balls for any other ball. And this means that there exist points for which U epsilon is isometry on the points. So there exists Xij perhaps I will write them as XRS epsilon and XSR epsilon. They belong to the balls. For which we have the isometry of U epsilon. Fine. And then, well, this is U epsilon is a sequence of one Lipschitz maps. We can pass up to we can subtract a subsequence that converges locally uniformly. And this condition will mean that for the limiting one Lipschitz function, the one Lipschitz function will be isometric on the points x1, x2, x3. So we assume that u epsilon converges to u naught, and u naught, by this condition, it follows that u naught is isometry on x1, x2, x3. Okay, and now the question is what points we choose to get some contradiction. We'll just pick some 3 collinear points. Actually, it suffices to take collinear points. So that x2 is equal to tx1 plus 1 minus tx2. Then, because of the strict, x3, thank you. And then because of the strict convexity of the Euclidean sphere, then u naught, which is an isometry on the points x1, x2, x3, is necessarily linear. Then f of x2 is equal to t f of x1 plus 1 minus t f of x3. And then we may extend f to an affine and one Lipschitz map on Rn, and what we can conclude is that if we look at the integral of u naught, so we'll look on the integral of u naught against nu naught. The integral of nu naught against nu naught is precisely this sum. And this, as u naught is one Lipschitz, this is bounded from above. This is bounded from above. So one thing that I should have said is that if we take such a limit, then u naught will be necessarily a maximizer for nu naught. And as we have seen, it will be an isometry. So what I would like to write here is that if we take any one Lipschitz function, then such an integral with respect to nu naught will be bounded by similar integral with respect to all one Lipschitz and affine functions. Where f is affine and one Lipschitz. And this holds for any one Lipschitz map U. This follows from our assumption that the conjecture holds true, and this holds for any one Lipschitz map U, these points x1, x2, x3, and any v1, v2, v3, which are sum to 0 and are in general position. But then, by the continuity and by the density of points in general position, this actually holds true also for any v1, v2, v3, which sum up to 0. And now, what kind of v1, v2, v3 we take? We take the ones for which this will turn out to be 0. And when it turns out to be 0, it turns out to be 0 when we take, so let me put here, let's say, okay. So we'll take v1 to be equal minus tv, v2 to be equal to v, and v3 to be equal to minus 1 minus t v. And this is because of the affinity of f, this will be 0. So then we infer that this is 0 for any, this is bounded by 0 for any vector v like here. And this means actually that if we put what's here in there, what we'll see that u of x2 minus t u of x1 minus 1 minus t u of x2, scalar product with v, is it visible? Is bounded below by 0. Bounded from above by 0. And this holds for any vector v. So therefore, this has to be 0. And we have inferred that any one Lipschitz map on Rn has to be affine, which is an absurd. So this completes the disproof of this conjecture. Okay, I think this is all what I had to say. So thank you very much for your attention. And here are some perhaps papers. Thank you.
Yeah, thank you very much for the interesting talk. Are there any questions?